My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the magnetic field of the electric current. Movement of charges create magnetic field. In this edition, we'll be able to learn about the magnetic field due to current carrying straight wire, current carrying circular coil, and solenoid. So let's get started. The magnetic effect of the electric current. In 1819, Hans Christian Ørsted discovered that a wire carrying an electric current, was able to deflect a magnetic compass. Okay, it is shown in front of you. And this means that flow of a direct current in a wire, in a conductor, produces a magnetic field. It means that the movement of charges, creates a magnetic field. Basics on magnetism. What's meant by a magnet? A magnet is a substance which has a magnetic field. Once again, a magnet is a substance which has a magnetic field. And what's meant by magnetic field? Magnetic field is the region surrounding the magnet in which its magnetic effect can be detected. It is the region around the magnet in which the magnetic effect can be detected. The magnetic field is composed of magnetic flux lines. Magnetic flux density at a point is denoted by B capital, and we want to give it a definition. So definition of magnetic flux density at a point. First of all, it is determined by the expression, by the relation phi over A. Phi is the magnetic flux, B is magnetic flux density, A is the cross-sectional area. So magnetic flux density is numerically equal to the number of flux lines passing normally through unit area at that point. It is equal to the number of flux lines passing normally through unit area at that point. Since beta or B is equal to phi over A, so magnetic flux is equal to the product of A, B. A is the cross-sectional area, B is the magnetic flux density. In general, phi is determined by or from the expression AB sine alpha, where alpha is the angle between plane of the coil and magnetic flux lines. Alpha is the angle between the plane of the coil and magnetic flux lines. In front of you, we've got three cases. This is the plane of the coil. If magnetic flux is perpendicular, magnetic flux is given from the expression AB, product of AB. If it is parallel to the plane, the flux, is equal to 0. Then, okay, what if it makes an angle alpha with the plane? Of course, in this case, we'll make resolution. Component, close to the angle, it will be beta cosine alpha, and that perpendicular, it will be B sine alpha, and of course, we'll take the one which is perpendicular, phi is equal to AB sine alpha. Okay, this is the general expression, can be applied on the three cases. AB sine alpha. In the first, it is AB sine 90. Sine 90 is equal to 1, so it will be just AB. In the second, it is AB sine 0, and sine 0 is equal to 0, so phi will be equal to 0. Okay. Units of magnetic flux density. Units of magnetic flux density. Beta flux density equals phi over A. So Tesla is the unit of magnetic flux, and it is equal to Weber over meter squared. Also, later on you will be able to know that Tesla is equivalent to Newton per ampere meter. Newton over ampere times meter. And now talking about properties of magnetic flux lines. Flux lines never intersect each other. They never intersect. Okay. Also, flux lines are imaginary lines. They tend to contract. They tend to contract. They tend to shrink. They tend to repel one another sideways. They tend to repel one another sideways. The direction of the magnetic flux lines can be detected by the direction of a north pole of a magnetic needle of a compass. And now talking about magnetic field due to a current in a straight wire. Magnetic field due to, yes, current carrying a straight wire. We've got a straight wire that carries an electric current, and we'll talk about the magnetic field produced due to the flow of the current. The lines of the field are a series of concentric circles. Concentric means they've got a common center, and the center is the wire itself. So the lines of the field are a series of concentric circles with their common center at the wire. The plane of the field lines is perpendicular to the wire. This is very important, and it is shown in front of you. The field is composed of, yes, concentric circles. They are crowded near the wire. They widen apart as we move away from the wire. Plane of the flux lines is perpendicular to the, yes, to the wire. The direction of the field is practically determined by using a plotting compass. Also, the direction of the field can be determined by using one of the following rules. Ampere's right-hand rule. What about it? Okay, if the wire is grasped in the right hand with the thumb pointing in the direction of the current, conventional current, of course, the curl of fingers, direction of fingers, will give the direction of the magnetic field. Once again, imagine the wire to be grasped in the right hand with the thumb pointing along the wire in the direction of the current. The direction of the fingers will give the direction of the magnetic field. This is the first rule, theoretical rule, to be used to determine the direction of the magnetic field due to a current carrying a straight wire. Also, we could use Maxwell's corkscrew rule. We call it the right-hand corkscrew rule. Maxwell's corkscrew rule. What about Maxwell's corkscrew rule? What about it? Okay. It states the direction of rotation of the corkscrew gives the direction of the magnetic field if the corkscrew is driven in the direction of the current. So let me say it. Imagine a corkscrew being screwed along the wire in the direction of the current. Okay. The direction of rotation of the screw gives the direction of the magnetic field. And now we've got, yes, a convention which is very important. And now we've got a convention which is very important talking about the fields. And it is, yes, used everywhere. It is international language. It is the dot and the cross convention of the direction of the current. Okay, in front of you, we've got something here. We've got, yes, the symbol X means we've got a wire and the current is passing into the wire, down into. Okay, the field will be in the figure shown in front of you. Okay, this is the convention of X. X means down into. And what about the convention of dot? It means out of. So X means current direction is down into the page or down into the screen. And dot means it is out of page or out of screen right now. Okay? We've got something very important here to mention. It is about the direction of the field. Direction of the field depends on the direction of the current. It means if we reverse the direction of the current, direction of the field will be reversed. So once again, direction of the field depends on the direction of the current. Magnetic flux density beta at a point of normal distance d from the wire, okay, can be determined from the expression. Okay, right now we want a relation that gives magnetic flux density at a point, at a normal point, okay, from a current carrying a straight wire. Okay, beta is given from the expression beta is equal to mu I over 2 pi d. Okay, I is the current intensity. D is the, yes, normal distance between the point and the wire. The point, you want to calculate the magnetic flux density at it. So mu is the magnetic permeability of the medium, separating the point and the wire. When the medium is air, permeability equals 4 pi times 10 to the power of -7. Web, yes, ampere -1, meter -1. In this particular case, we can say beta is equal to 4 pi times 10 to the power of -7 I over 2 pi d. 2 pi will be crossed with 2 pi, okay? So we will obtain 2 times 10 to the power of -7 I over d. So once again, we'll use this particular relation, beta is equal to 2 times 10 to the power of -7 I over d when we've got a wire in air. Okay, the expression beta is equal to 2 times 10 power -7 I over d. Talking about total magnetic flux at a point between two wires carrying currents in the same direction. So we've got two wires that carry currents in the same direction. And we want to calculate the total magnetic flux at a point between the two wires or outside the two wires. Okay, so once again, in front of you, we've got two wires carrying current in the same direction. Fields outside the wires have the same direction, but it flows in opposite direction between the two wires. Okay, so between the two wires, the two fields are in opposite directions. So B total is equal to B1 minus B2, when B1 is greater than B2, or B2 minus B1 when B2 is greater than B1. Okay, talking about the total magnetic flux at a point between two wires carrying currents in the same direction. Between the two wires, fields are in opposite directions. Outside the two wires, the two fields are in the same direction. So B total will be B1 plus B2. And what if we want to calculate the total magnetic flux due to two wires carrying currents but in opposite directions? Okay, so in front of you we've got two wires carrying currents in opposite directions. The fields outside the wires will be in opposite directions, but between the wires they will have the same direction. Okay, between the two wires the fields have the same direction, but outside they have opposite directions. Okay, so total magnetic flux at a point between the two wires, B total equals B1 plus B2. They have the same direction, so we just add both of them. But outside the wires, total magnetic flux, yes, will be, since they are in opposite directions, okay, so it is B1 minus B2 when B1 is greater than B2, or B2 minus B1 when B2 is greater than B1. And now talking about something very important, how to locate the position of the neutral point. Locating the position of the neutral point. It is somewhere in between the two wires when they carry currents in the same direction. Neutral point is located, situated where the two fields are in opposite directions. So when the two wires carry currents in the same direction, it will be between the two wires. Two wires in front of you carry currents in the same direction, currents I1 and I2. So the fields between the two wires are opposite, so we expect to find a neutral point. Okay, distance between the two wires is denoted by D. Let the point to be located at a distance x from one wire. It is at a distance x from the wire carrying the current I1. So it is a distance D minus x from the other wire. The two fields are in opposite directions, so B total will be the difference between the two fields. So B1 minus B2 is equal to 0, or B1 is equal and opposite to B2 to obtain a neutral point. So mu I1 over 2 pi x is equal to mu I2 over 2 pi between two brackets D minus x. And of course, mu will be crossed out, 2 also and pi will be crossed out. So we can say I1 over x is equal to I2 over D minus x. Rearranging this in a better way, we can say I1 over I2 is equal to, yes, x over D minus x. This is the relation to be used to determine the position of the neutral point, to locate the position of the neutral point. Also, neutral point lies closer to the wire carrying the weaker current. This is very important, and you should keep this in your mind. Neutral point lies closer to the wire that carries the weaker current. Neutral point lies outside the two wires, okay, when they carry currents in opposite directions. Okay, and also it is closer to the wire carrying the weaker current. in front of you, we've got two wires. Front of you, two wires are shown, and they carry currents in opposite directions. Currents I1 and I2, two different currents in opposite direction. Fields between the two wires have the same direction, so we cannot find a neutral point. The neutral point will be outside the two wires, closer to the wire carrying the weaker current, okay? Fields outside the two wires are in opposite directions, so we expect to find the neutral point outside the two wires. Distance between the two wires is d. Let the point at a distance x from the wire carrying the current I1, okay? And I2 is greater than I1 because we located the neutral point near I1, okay? And once again, neutral point means we've got two fields equal and opposite. They are equal. Okay, so B1 is equal to B2. So mu I1 over 2 pi x is equal to mu I2 over 2 pi between two brackets d plus x. Okay, so I1 over x is equal to I2 over d plus x. And instead of d minus x, it will be d plus x. So we can say I1 over I2 is equal to x over d plus x. And now, talking about the factors affecting the magnetic flux density of the magnetic field of a current carrying a straight wire. What about the factors? And of course, they are, yes, taken or known from the relation that gives the magnetic flux density. Beta, which is equal to mu I over 2 pi d. So, the current intensity, this is the first factor. The normal distance from the wire, and it is denoted by d. And permeability of the medium surrounding the wire. Permeability of the medium surrounding the wire. And now talking about magnetic field due to a current in a circular coil. Due to, yes, current carrying circular coil. Okay, shown in front of you now. Circular coil. The current flows in, yes, clockwise direction. Observe the fields. It is uniform at the center of the circular coil. Okay. So we've got a circular coil that carries an electric current. Okay. The field lines run in loops from one face of the coil to the other. The field is similar to that produced by a short bar magnet. The field is similar to that produced by a short bar magnet. And the coil acts as if it has a north pole on one face and a south pole on the other. The magnetic flux at the center of the coil, as I said, is straight and is perpendicular to the plane of the coil. And now determining the polarity of the coil. What does it mean, determining the polarity? It means knowing, yes, which face acts as a north and that acts as a south pole. Polarity of the coil can be determined by various methods. Okay, first of all, if the current flows in a clockwise direction, we expect a south pole. If it flows in anti-clockwise direction, we expect, of course, a north pole. So once again, the face of the loop where the direction of the current is clockwise behaves as a south pole, and the face of the loop where the direction of the current is anti-clockwise behaves as a north pole. Also, we can use the right hand corkscrew. The question is how. When a right hand screw is screwed in the direction of the current, of course, the direction of the conventional current, the direction of turning, direction of fastening, gives the direction of the field at the center of the loop. Also by using a plotting compass. The magnetic flux density at the center of the circular coil is uniform. And what does it mean it is uniform? It means we can determine its value by using a relation, an expression that gives its value. Yes, magnetic flux density equals mu, which is permeability, Ni over 2R. N is the number of turns on the coil, I is the current intensity, and of course R is the radius of the circular coil. If the coil is air-cored, then beta is given by 4 pi times 10 to the power of negative 7 Ni over 2R. And now talking about the factors affecting the magnetic flux density at the center of a circular coil. The factors are, of course, are known from the expression. So first of all, the number of turns on the coil. Magnetic flux is directly proportional to the number of turns. And this happens only when the rest of factors are unchanged. Second factor is the current intensity. Beta is directly proportional to the current intensity. And it is inversely proportional to the radius of the coil. And permeability of the core, permeability of the medium inside the coil. Your attention, please. Total magnetic flux at the center of two concentric circular coils. If we have two concentric circular coils that have the same plane, and we want to calculate the total magnetic flux, it will be B1 plus B2 when the currents through the two coils are in the same direction. And the difference between the two fields when the currents are in the opposite directions. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.